Now, better? Okay. It used to be a time when I used the microphone, people complain I was too loud. But now we are, no, keep on talking, that's okay, it's all boring here. Okay, we are on our quest to try to explain to you how to make processors. And slowly, last week, I was talking about assembly instructions, and I don't know how much convinced you were, but they didn't really look like program things. They were like R-type, J-type, I-type, some strange things. And what my goal is this week, I will try to convince you that those things that look a little bit weird can actually translate very well the constructs that we know from programming. Mainly, we can see how we can make branches, we can see how we can make loops, the program control flow components. And then the more important part, the more interesting part is how we can translate function calls using these things. And we will have a couple of fun examples. Tomorrow, I will probably fall flat on my face. Great entertainment for you. Well, it's good if I manage it, but if I don't manage it, at least it will be funny for you. And I will try to convince you that those things, those instructions that we have seen are actually sufficient to have any kind of program to execute, which will be great news because the following week, what we will be doing next week is going to see how we can implement these instructions in hardware. We are going to build our first microarchitecture. We will implement the key instructions. We won't implement everything. We will implement a few key functions, and then you will realize that, hey, I see how this is going, and if I write a few more lines of code, this will do it. So this is going to be next week's lecture, and then we will stop and have a little bit of discussion about how well this processor does. Because what we will be doing, also didactically, we will keep it very simple. We will make a lot of simplifications, and then we will want to understand how well this performs. Then we will see that we could do some tricks to make it faster. That's when things start getting interesting. We will keep actually this thing the same. We will just explore some options to, without too much effort, how to get more performance out of it. We will see things like pipelining and make our architecture slightly different with very good beneficial results for us. And then, well, then we will open a large can of worms because every type of trick that we have will have some consequences. So nothing is for free. You get some very decent speed ups or performance, but you will also have to be prepared to pay the price. And we will see this. Then the lecture will go on more and more and more elaborate processor architectures so that you can also understand what the latest, greatest processors look like. So I hope you have something to look forward to, and that helps you get through this particular lecture. Let's get going. First, I need to make a brief review of what we talked about last week. And we will start talking about programming, how to make these things. And at the very end, at the end of the lecture tomorrow, we should see how everything comes together from a high-level code. How do we compile it? Where does it end? How is it placed in the memory? What are the components of it? Hopefully, that's my goal. Within the next 90 slides or so, we will get through this. So the slide set, we already had it up for last week, just in case we went too fast. So we had a, okay pace. So this week we entirely dedicate to this one. So just to recap, we said that the computer has a small vocabulary, and the vocabulary is called instructions. Those are the words the processor understands. And the set of them together, so the entire dictionary of the words they understand, is called an instruction set. And that defines actually what the processor can do, how it will operate. Now, what we will end up doing is translating our high-level code in C, in Java, whatever, into these instructions. And the compiler, assembler, whatever, the tool chain in between will take care of that. When you talk about it, you see assembly language, which is a more human readable form, although you might argue whether or not this is really human readable, but at least it's not only zeros and ones, is the human readable form of the format of instructions. And the machine language is pure zeros and ones. It looks like data, but if you know that it's an instruction, we learned and we discussed a little bit about it. You can interpret those zeros and ones as things that the processor understands what to do with. And what we will be covering is the MIPS architecture. It's one of the more modern RISC-reduced instruction set architectures that puts a lot of emphasis on simplicity, which is great for teaching. It actually originated as a tool for teaching. And today's ARM and RISC-V architectures are further developments or reimaginings of this thing. And it doesn't really matter which architecture you learn, as long as it is understandable and basic. Moving from one to the other one is not so difficult. Why do I have MIPS and not RISC-V? Well, we are lazy. We had this lecture for quite a while. All the slides, all the exercises were in MIPS. At some point, we will have a reset and maybe change the architecture. The teaching content, the didactic content will not change. So we also discussed that a lot of what we do is moving data back and forth. The operations aren't that spectacular. But the problem that we have is when we have data in our memory, which is a large array structure that you store here, it takes a lot of time to access them. It takes sometimes 50, 80, 100, 1,000 cycles of the processor to go and fetch a piece of data from the memory. Since it is so slow comparatively, we say we have some a small set of registers right in the processor. Those registers are right under our hand. It's a small set. MIPS has 32 of them, and we can use them immediately. What we do is, with 32 registers, we cannot do that much. So we have instructions that allow us to copy data from the memory into the registers. And once we are done, once we have computed something, stored it in a register first, we can move it back to the memory. We call these architectures load store architectures because they do not have instructions that allow us to directly interact with the memory. There's always this register in between. The good news about it is, because we only have a limited set of them, hey, there's only 32 registers I can deal with, and I only need 5 bits to tell which register I'm dealing with. And then we said MIPS uses 32 of them. And by the time it was made, that was a lot. It's like, oh my God, 32, are you crazy? And so what is being used is a convention saying that, hey, some of those registers we can use for general purpose things. We have like our safe variables, we have our temporary variables, we have our procedure arguments, return values, whatever. We will have an understanding that since there are so many, let's make sure that everybody who uses this thing, writes programs on it, agrees on using certain registers for certain things. Now, there is one special one. Well, there are two special ones actually. Register number 0 contains the value 0, and you cannot write to it. It will always be 0, which is weird. And then we have 1, which we will talk about a lot today and tomorrow, is the procedure return address. It's a special type of register. If you want, there's also the stack pointer, SP. That one is also one that it's not embedded in the instructions, but has also some special meaning. So we have a lot. Because we have a lot, we can specialize a few of them to help us go through things. And yeah, what we want to do is, this is a summary of it. There is too much data that can fit in only into 32 registers, so we use a larger memory. The memory in MIPS, the ones we are looking at, everything is 32-bit, so memory has 32-bit addresses. If it has 32-bit addresses, you have 4 billion locations where you can put something, 4 billion 32-bit words. That's a lot. And it's large. It can hold a lot of data, but it's also slow. So we use a combination of data in the memory and registers to get around. Now, this is a choice that was being made while the computer architects sit on a table and try to say, I don't like the current processors. I want to do something else. I want to do something new. So this is computer architect's job. They are saying, I want to come up with something new. Once I come up with something new, hopefully the entire software ecosystem, compilers and other things will follow suit. At the same time, because there's an agreement on the instruction set architecture, while the software tool chain is being provided, the hardware people can work on implementing it, creating the microarchitecture that will work on those instructions and make them a reality. Now, with MIPS and RISC in general, the idea was that we need to take a little bit more into account what the limitations of hardware are. So they wanted to, that's a choice. That was a choice that was made by the designers, and they said, I want to have some design principles. I want to keep things simple. I want to make the common case fast. And instead of having a lot of complex instructions, I'll just use the very minimum I need. I'll implement them well. And if I need to do something a little bit more complex, I'll just use a few of those instructions. On average, I'll be winning because my small instructions will also, most probably, be efficiently implemented in hardware. I can do things very, very fast. And if every blue moon I need to do a really complex operation, instead of using only one instruction, I'll use it doing 2, 3, 4, 5, whatever. They are rare anyway, as long as I can do things fast. And we sat down and said, okay, let's take a look at the type of instructions we are making, and we introduced 3 types of instructions. So the first one we called R-type because it only operates on registers. It's a very common operation when you for example, do addition. You have A plus B goes to C. So you have 2 source operands that somehow go a transformation, and then they are written to a destination. And since everything is in registers, why don't we have 3 registers that will do it? So we have 32 bits, and our goal, secret mission, if you want, was make sure that every instruction we have fits into the 32 bits. Is that ideal? No. But if we can manage it, if we can make some compromises, then the life of whoever is interpreting these instructions is relatively easy. Every 32 bits is a separate instruction. Once I have 32 bits, I know exactly what to do. I don't have to do any special cases, exceptions, and things like that. So 32 registers, I need 5 bits to tell each one of these. So I have 5 bits for RS, 5 bits for RT, 5 bits for RD. That's 15 out of 32 is gone. Now you look at it and you say, okay, I have 17 more bits. What shall I do with it? And then we say, yeah, you know what? We need to differentiate between different things. There's addition, there's subtraction, there's R-type, I-type, J-type. And they said, okay, look, let's just use those 6 bits at the very beginning. It's, like the first few bits. Let's tell them what type of operation it is. And, by the way, if it's R-type, that operation is 0. 0 says, let's, this is an R-type operation. Okay, I have my R-type operation, I have my RS, RT, RD, but how do I know whether or not I'm adding, subtracting, ending, whatever? They say, we are going to add another 6 bits at the very end. Why not? It's a choice. And that one is going to say what type of R function are we implementing? Is it an addition, subtraction, something, something? And then there is this shift amount. We didn't even discuss about it so much. We add extra bits, and we say, hey, if we make shift operations like to left, shift right, we can encode how many bits we want to shift. And 5 is a nice number, round number. 2 to the 5 makes 32, so I can maybe have any shift amount encoded in it. We didn't discuss about it much, but it's more or less a detail and opportunity to do something. We didn't need many more bits. 5 were left over. Great, let's use it. Questions so far? Fascinating story, I know. So, some examples. This is what it looks like. We said, hey, addition, subtraction at the very top. You see add. What am I adding? I'm adding the register called S1 and the register called S2. The contents of them are being added to the and the result ends up in the register S0. They don't need to go in this order. I could have added them in any way, but the operation, as I said, all R types are 0. Then come the register, so register number 17, 18, 16. What? How? Well, we were discussing that, right? So S0 is 16, S1 is 17, S2 is, that's the address of the register. Okay. We are not shifting anything, and then there is a function. So 32 apparently is add, and 34 is sub. And what would happen? Well, I could then translate this. This would be the assembly code. From the assembly code, I could get to these numerical values. I can translate them to binary. So the op code is 6 zeros, 17 is 1001, 10010, 100. The shift amount is 0. The function is 32. And then I have my binary machine code result. So in hex, so this 0x stands that the rest of it is in hex. 02, 32, 80, 20 means add whatever is in register 1 to whatever is in register S2 and write the result to S0. That was it. And we said, hey, that can implement a number of instructions. Then we saw that, not all instructions need 3 registers. We saw that there are a lot of cases, or we argued, I'm not very sure if you agreed, we argued that there were a lot of operations where we might need a constant. I want to add a constant value to something that's in a register. We said we call these constants immediates. And for the immediates, we say, hey, I can have source registers, add something to it, and then write the result back to another register, and I could have a number of operations like that. We saw add immediate and things like that. Then the next thing that we saw, which was a bit confusing, was these load words and store words and things like that. So we were talking about writing things to the memory, and I'm looking for the light just to, almost made it. Just to refresh your memory, we had things like load words. We said we want to load a word from the memory. We had some register, let's say T1, and then it got a little bit weird. We had an immediate, something like 44, and then we had another register, which was something like S0. Say what? I say every memory, every data in the memory has a location. That location is a 32-bit address. And the address, instead of writing directly the address, we are using a lot of indirection here. First, we say, look, there's a base register. Whatever is in S0, let's read this out. And on top of that, let's add this constant, in this case, 44. And that thing will then show me at what location the data is. Now, let's go to that location in the memory, which is a large array. Let's go to this address, pick whatever value is there, and then write this. So this is whatever is in S0 plus 44 gives me the address, and then I pick the memory location, whatever I find there, and write it back into T1. Store word is the same kind of operation. It's then opposite. Whatever I have in the register will be written into that memory address. And we realize it has a similar I-type operation. I have 2 registers. Here RS and RT, and I have a constant. Now, this looks like showing my ear like this, and it is in a sense. The reasoning behind this was actually quite simple. We said, we don't want to make too many instructions. And if I can realize the things I want, even though the instruction may look a bit weird, I'm okay with that, because I'm going to implement one instruction. I'm going to make that really well. Instead of making 5 different instructions, maybe some where I don't need an immediate, maybe one where I don't need a register and have 3 different versions of it, I'll just use one. And this is also the reason why this 0 comes up a lot. We have a number of operations where, we don't want to use a value, but we don't, we need a useless value so that I can go through the instruction. And 0 happens to be that one in a number of cases. So what happens after that? We have the 32-bit instructions, and data is stored in the memory. They are indistinguishable from each other, whether or not you have a cute picture of a cat or a complex program running some crazy algorithm, or your telephone address book, whatever, they will all be zeros and ones somewhere in the memory. The instructions that actually are the program are located at a place as a sequence of instructions, and you can just load it somewhere in the memory and then let the processor know where to look for them. And the processor fetches and reads these instructions one by one and looks at what it says, those zeros and ones. Oh, I'm adding, I'm moving, I'm doing this, and then goes away. The question was, where does he find what he has? And we say we have a special counter that's not part of the registers, and that counter shows me in memory where I should start fetching the instructions. Normally, he will go one by one. So he goes to the address. How do I know where I start? Well, it's already agreed upon, a gentleman's agreement if you want. Whenever you press the reset button, the program counter goes to this weird address. So whatever you do, the first thing that boots in the memory, in the processor, should be located at this address. Reset, release it, look at the 32-bit value, bring it to the processor. What does it do? I want to add this thing and this thing. Okay, great, we did that. Now what? Pick the next address, do something else. So this is how things were going. Once again, we didn't talk about how we come to the assembly code. We will learn this at the end of this week. But we ended up with a bunch of instructions in assembly. If we translate them, we just saw that this is possible. We ended up with some hex code. We loaded them into the memory. Funnily enough, they're upside down, right? The 8C is here, the 023 is here, 226 is here, etc. And this happened to be the first location where the processor goes through the reset. The program counter will show here. We'll do the glorious operation of, what is he doing? Load word T2 32-0. That seems to be the first thing that comes into his mind. And the reverse is also true. If you are like a James Bond kind of hacker type, and you receive these ones and zeros, like this 02F34022, you can just write down the binary translation of it, 02F34022, and then from this you can go to the field values, say op0, well, op0, that must be an R-type operation. Let's look at here, 34, that's a subtraction. So if you are subtracting, what are we subtracting from what? And then you say, okay, there is like, this is the S3, this is the, well, I have no idea. And you figure out which one is which, and then you have your instruction. This is what we covered in a nutshell last week. Any questions, any doubts? Who wants to, yeah. No, I mean, this memory, yeah. This goes to the main memory, to this big memory, like this one. You know, it's continuous. It starts from 0, 0, 0, goes all the way to whatever, FFFF0. And out of this, you are going to get a 32-bit value. It will be between, like if this is the very bottom of the memory, 0, 0, 0, 0, and this is the very, very top, FFFFFF, right? This thing here is a 32-bit value. Let's say it is I'll just make it up, right? It's 08, never do this at home. It's, well, there's one more 0, 08000000. Let's just assume this was already in here. I'm going to add 44 to it. So we are going to 080000. I got lost. 40. Let's assume this is hex for some reason, okay? So that my example works. And we go to this memory location. And here the secret number, the answer to everything is written, right? 42. And this value will end up, this value will end up going into T1. You would want to, technically, what you wanted to do is something like this, load word into T1, the address, let's say 08000044. This is what I wanted to do. I mean, in the end, this is what will happen. I don't know if I'm confusing or, yeah? No. No. I mean, if we did, I'm sorry, I was drunk. I shouldn't have said that. Happens, not that I'm drunk, happens that I make mistakes. Also happens that I'm drunk, but not in the class. So this is what we want to do. And the problem here is, if you want to write an instruction like this is already 32 bits. And I want that the instruction fits into 32 bits. How can I make this? And so, when you go to programming type of things, you will realize that we usually don't want direct physical addresses. We want things relative to where we are. We want, we will see, this is part of today. For example, we have a data structure, which is an array, which is a start location. And then I will want to iterate over that array. And, you can say that, hey, this is the start of the array, this is the index within the array, and I want to move inside it, rather than always writing the absolute location of the memory I'm accessing. Well, very good question. An important question to answer, by the way. Anything else? No? So we covered this. Now, these instructions that we had were kind of okay, but they didn't really cover the things that are needed if you want to do something more interesting, because the programs that we know are usually not going one instruction after another. That's not the fun part of it. The fun part is when we are making decisions based on some conditions. Did the user press OK? Or did I count up to 1 million? Do I, continue making this? So we have things that control the flow of the program. And we are calling, we have two main parts of it. One of them are what we call conditional branches. We have two options. If this, do that, else do something different. That would be a conditional branch. And for that, we have two instructions. One of them is branch if equal, and then it's dual is branch if not equal. And we will see there are I-type instructions. So we didn't look at all I-types. And then we have unconditional branches. Those are which we call jumps. That's not if or something. When we come there, we are going somewhere else. And we have three different versions: the jump register, jump, and link. And we already said that we have like this jump J-type instructions. Nice detail. The jump register is not a J-type instruction, but the jump and link and jump are the only J-type instructions we have. You will see, hopefully. Okay. Are we stoked and interested? So let's try to see a little program, and let's try to see what is happening here. Now, what I'll try to do, let me see if this works. It will be an experimental thing, especially for tomorrow. I'll try to switch to this guy. It's the exact same slide. I'm just trying to, I'm not reaching them. So this is why I'm switching to the Docker cam, hopefully. Oh, yeah. And now we have to do this. We agree that it's the same slide, right? Oh, it's even better, it's bigger. I should be presenting it like this. Okay. So, what is happening here? Oh, yeah, question. No. Question? I was not even listening. I guess that's not a question. No? No. Okay. So eager to answer questions. Okay, so what is happening here? Let's start at the very beginning. Nothing interesting is happening actually here at the very, very top. So I have these couple of instructions here. Yeah, I made it myself, okay? It's funny. No, okay, come on. So the first part is just showing you I'm just initializing, loading a value into S0. What am I doing? I'm adding 4 to the register 0, that will make 4, and I'm copying that value into S0. All I do is move the value 4 into the register S0. Okay, there's nothing very entertaining about it. I'm doing more or less the same into the next one. I know it looks, you see, this is the point. It looks pointless. It looks like I'm doing an operation just to move this thing. That helps me keep the type of number of instructions down. If I want to move a constant to a register, I can just add immediate to the register 0, the constant. And since register 0 is always 0, I'll add 0 to a number and write it down to the register, so I don't have to make 2 different types of things. Now, when you're looking through the slides in July, you will ask yourselves, what is going on here? So this is shift logical left, take the value in S1, shift it, the shift amount, by 2 to the left, and write it back to S1. It's a very fancy way of writing also 4 into S1. Now, in case you're looking and watching this in July, it doesn't make too much sense. We just want to emulate, let's say, a number of operations that could have happened. And since we don't have much space on these slides, we are keeping the program short. It's just an example. It stands in for any kind of operation. Now, but if we did this, you realize that S0 is 4 and S1 is 4. And now we come, I mean, they are both 4. And now we come to this point where we are making a check between S0 and S1. And we say, if branch if equal, if both S0 and S1 are equal, let's jump to wherever we call the target. Are they equal? Who says equal? That part? No. Okay, Insta pages. Okay. Where is target? Well, the target is a label that tells us where in program we should jump. So we say that the branch is taken. We have to jump all the way down here to the target. And then the next instruction that we will be executing is this one. And here, if I can get this right, is I add S1 to S0. One of them was 4, the other one was 4, and the result will be 8. We have jumped over these other instructions. So this is one of the ways how we will implement a number of the instructions or of the constructs that we have in programming. So just to show you that it's exactly the same slide. And there is also the brother, the sister, the same thing. Now we are making branch, if branch not equal to jump to target. Now, in this case, because they are equal, we will not jump. We will continue with the next line. So we will add immediate 1 to S1, and then we will subtract S1 from S0, and the result will be 1. And now I'm back to this location. Notice that nothing says don't continue. So I will continue doing it, and I will add S1 and S0. One of them ended up being 5. No, I made a mistake. One of them, S1 is, at the moment is 5, the other one is 1, so this is wrong. 1 plus 5, it should have made 6. Doesn't matter, it's just standing in for the operation just to explain what kind of branches we can make. Questions? Oh, yes. Oh, we will come. I mean, the assembly, but it's a very good question. Like, what is target, is this thing? Notice that this is assembly. This is so that we can read and understand it. Once it's translated into machine language, ones and zeros, these things will be different. What will change is, this thing will be, let's say, an offset to the current location, either positive or negative, and that one will manipulate the program counter. So next time the program counter is fetching something, its address will end up being manipulated. So this is what will happen. But we are going there. Yes? Yes. Just a few more slides. We are getting there. But very good questions, you know. You said, hey, I want to maybe jump over this thing. And sometimes, so these conditional branches are great, because essentially it can allow us to make any kind of condition in for loops, while loops, if then else clauses, cases, etc. But sometimes we have to say, you know what, we are jumping no matter what. And this is one of those issues we are doing. I mean, the program is slightly different, shift right arithmetic, okay, why not? Target. And we come to the third line, which says jump target. The moment we see it, the next instruction that's executed is this one. We jump over the SRA, ADI, and sub, and continue from here. That's the one where we are jumping directly. Yes?
Why would there still be instructions after jumping? Because
oh, you'll see. It's going to be fun. Yes, happens a lot. Yes? Yeah, we will come to that. You'll just have to excuse me for a few hours. It will come quite at the end. Normally, when you execute, let's say, when you are here, you have the program counter point to the next guy. And then when you execute this one, you have the program counter point to the next one. They are all addresses in the memory. And what we are going to do when we jump is manipulate the program counter. We are either going to give him a relative address, meaning, hey, normally the next instruction you would have executed is at this address, wherever that is. And we are going to say, instead of going there, go 10 further, go 15 back. That's one version. The other version is, like this one, we will exactly tell him where to go. You know what? Go to address whatever, 008000044, whatever it is. And you say, oh, you know what, I'll just go there. He told me to go there. Great questions. Love them. See, in July, you can't ask questions. Okay, so maybe this is slowly trying to answer. Just a second, I might have jumped one. Now, there is also the jump register one, which we will use actually quite a bit. The jump register one is a little bit entertaining. Now, the first line you see is running at 2000, about hex 2000, right? We somehow managed to load into S0 this value 2010. Now, the register contains this value. The next instruction says, jump to wherever the register is pointing. Now, this one, in this case, is a wallet address. It's 2010. And if you look at it, it's this location. So the next instruction that will get executed is the load word 44 plus S1 into S3. So he jumps to the location pointed to by the register that you supply. Now, this will come very handy. More useful in many cases than the one where we have the direct address. Okay. People still seem to be convinced. Oh, sorry.
The register, we mean the actual, not like the value that it holds, right?
Yes.
That address, like as the address.
Yeah, you know, the first line loads the value, adds this 16-bit value to the register 0. So the result is 000212010. So that's the content of the register. Then the next line jumps to the address. And it happens to be, we didn't want to write like a very, very long code snippet here, and he does that. So now these things combined allow us to do a number of very entertaining things. What we will see now in a short succession are how do these if, else, while, and for loops get translated into series of these instructions. So before the break, let's try to manage this thing. Now, on the left, I have the high-level code written in some arbitrary language, and on the right, I have the MIPS assembly. In order not to make too many data movements into the registers, you'll realize this is like half the program is moving data in and out of the registers, okay? Because we only operate on these 32-bit registers, and they don't magically appear there. We need a lot of the instructions to move data either from the memory to the registers or from constants be placed inside the registers through some of the tricks we will show also later on. Now, at the beginning, I have the comments that says, hey, these registers hold the values corresponding to these variables. Okay? So initially, magically, I'm not showing how this happened. S0 has F, S1 is G, S2 is H, S3 is I, S4 is J. And what I want to do is I want to see if I equals to J, then F is going to be G plus H. Later, I'm going to subtract I from F. Very reasonable thing to do. You know, I wake up every morning and say, let's write this code. So this is how it starts. The first one is comparing S3 with S4. Maybe let's do it this way. If I can find it. Give me a second. Do this. Let's switch to this one. It's the same slide. And let's try to find this thing. Okay, so what we are trying to do is we are trying to compare I to J. And if you look up here, I is S3 and J is S4. So these two guys go in here. And we are trying to see, hey, are these two equal? We are going to branch if not equal. Now, this is funny. This is the reverse, actually. If they are not equal, I'm going to go to L1. If they are equal, so this part is going to be this issue here. And then I'm going to, I'm sorry, this is the else one. I'm sorry. Can you forget this happened? Because I picked the wrong slide. So this is the one with if and else. Is that okay? I'm really sorry. This is the one with else. So if they are not equal, I'm jumping to here. And if I'm not equal, this is the else part that I need to run, right? So this is this part here. And if I'm equal, I'm doing this thing here. But now, that was the question that was coming. How do I need to jump over the else part. So this is what I'm doing. I check if they are not equal. If they are not equal, I do this part, which is here. And if they are equal, I did my addition, which is this thing. Now I have to jump over this so that I'm not also doing the else part. And for that, I say, hey, I know where the end of that program is, jump here. So I jump over one. Horrible. Sorry. Back to the slides. Okay, just allow me to finish. This one was the one where there was no else, right? So I was checking if there is branch not equal to, I go to L1, so I only do this one. If they are equal, I will be doing the addition. Now, once you add the else, so this is what was happening, the same exercise, this is what I was trying to draw there, is because this part is only executed if I is not equal to J, I run this, and then I jump from the previous one over it. I'll try better after the break, and let's meet at 1:15. We are coming to that. Okay. Where were we? I messed up the if statement. I was too eager to use this fancy thing. So from the questions I get, I realize that this interests you a bit more. Who is okay with these programming parts? More computer science, less electrical engineering. Yeah, let's go. It's a pity that I'm talking about it. Okay. So this was now the first example where we saw something that resembles more of the things that you are interested in and how it sort of kind of translate to that. There's still a lot of questions. We will come to them one by one. It just takes a few slides. So this was the if else, and this was one case, when I go back to this, where this direct jump made sense, right? Because we wanted to jump over some statement that was coming next, and by manipulating the program counter and saying, okay, I'm jumping over this part, so I execute the regular part, and I jump over the else part. So that is quite a common way of doing it. Now, while loops are also going to be very similar. So this is what we are trying to do. We are trying to determine the power of x such that, to the it's 128, whatever. So we have some initial values, and we say, well, the power is not 128. Take it, multiply it by 2, and then increment x by 1. That somehow doesn't make sense, but okay. Happens, not so important. So we have S0 is the POW, S1 is X, and at the very beginning we have the part that we are initializing. So what do we do? And this is now going to this is, well, I will probably mess this one up again. But, never give up, never surrender. So, you see that a lot of our life is trying to put initial values here. So what we are trying to do is we are trying to put 1 into POW, and POW is S0. So the trick that we are using is, let's use an add immediate. So the immediate is 1, and let's add it to the register 0. And this is not going to, and we are going to copy it to S0. So these things go in there, and I'm initializing the value. It's a long-winded way of just moving 1 into the register S0. Now the second one is quite funny, right? It looks very similar, although I'm doing something funnier. I'm adding the register 0, which is 0, to the register 0, which is 0, and I'm writing it to S1. Why? Yeah, well, it results in what I want to do. I'm actually clearing, I'm making sure that the content of S1 is 0 initially. It's exactly what we were also doing here. Do you see the difference? One of them was add immediate, $0 immediate. The other one is R type. One is I type, one is R type. Does it matter? No, they are both 32-bit instructions. In terms of MIPS, they are all equal citizens. There are sometimes choices when you are a compiler and you say, hey, I want to generate a 0. Which instruction do you want to use for clearing? Which instruction do you want to use for setting it to 1? They might have some preferences for whatever reason. It's not really that relevant. The next one is again one where we are doing the preparatory work, because we will want to compare the POW to the value to the constant 128. Now, it would have been possible if this branch and equal to had 2 immediates. But I don't have 2 immediates. I have 2 registers I can compare to, and then jump to a location, which is the immediate. So to be able to make the comparison to 128, I first have to copy this constant into a register, in this case T0. notice that since I have so many registers, and just to not confuse you, just to give you, or not to, or to make sure that you understand there's a lot of registers, I'm not always using the same one. So we copy it to T0, and then I can make a comparison between S0 and T0. Now, when I first go through this loop, S0 is going to be 1, T0 is going to be 128. And I'm checking if they are equal. They're not. Well, if they are equal, I would have gone to this part, and I would be done with the loop. Now, because they are not equal, I am continuing with the next line. And here, what I'm doing is the shift logical left. Somebody was asking me, why do we have an arithmetic left? Isn't the logical left and the arithmetic left the same? They are the same, and this is why in MIPS, you don't have an arithmetic left shift, you only have a logical left shift, because if you're shifting left, both logical shift and arithmetic shift are exactly the same. Somebody was asking the question while we were talking about shift operations a few weeks back. Shifting left, multiplying, you know, if I shift a binary number to left by 1 digit, I'm multiplying the number by 2. So this is exactly what we were trying to do. And now I am adding, I'm incrementing the immediate by 1, and I continue making this thing. I jump back to the while loop, check if S0 and T0 are the same. If they are not, I continue here. If they are equal, I'm done with the loop and I get out of there. Now, sorry. Doesn't work if I'm not on the slides. The one thing, so it's the same, different colors. The one thing that you should notice is that the assembler tests for the opposite condition. Here you are testing if you stay in the loop while they are not equal, whereas here you are trying to say, hey, if they are equal, let's get out of here. Otherwise, you know, the jump instruction will anyway complete the loop. Okay. Questions so far? If not, we are going to do the next best thing, which is for loops. Well, for loops are a little bit more. So there is initialization, condition, loop operation. And as long as, you know, we start with an initialization variable, check whether or not the condition is true, and increment it or modify that variable somehow. And then as long as this thing holds, execute something that falls into there. So you see this a lot. I don't need to explain this so much. So we start from 0. As long as we are not 10, every step we will increment it by 1. And inside there in the body, we are doing some sort of operation. Now, this one falls into the same thing. At the very top, you see that the compiler, we decided that whatever is I here will end up in S0. And whatever is sum should end up in S1. That's my mapping. I could have done S3, S7, whatever. And in the beginning, you again see that there's a number of things for initializing things. There's this S1 gets the first value, sum was 0. And then I also cleared I, because that's the initial value here. And then I need to, at some point, I need to make sure that the loop condition is checked. And since I need this to be in a register, I need to copy it from the immediate into the register T0. Now I have my loop. I'm just checking, am I done with the loop? First things, did I reach 10? Well, if I reach 10, then no need to continue. If I didn't, let's do what we are supposed to do inside the loop. In this case is adding I to the sum so that we can accumulate the sum. And then let's increment the loop variable and then jump back. Once I jump back, because I incremented it, I can already check, did I reach 10? No, I didn't. Okay, let's do it once again, jump back, do it again, back and forth. There you have it. Now, there are some funnier ones And this one is one of the funnier ones. Now we want to see whether or not, I mean, the loop condition is not the equal, because we have equal, we have not equal. And not equal wouldn't work here, right? I mean, in the previous one, here, it's a nice check. We want to continue with the loop as long, or we want to terminate the loop once the counter has reached 10. But if you say like less than this thing, we didn't really see an instruction for this. We very briefly saw it when I was talking about the ALU. And we need something funnier. So the funnier thing is this one, SLT. Let's use this part, very short. Set less than. Now, this is one of the funnier instructions, or one of the like, hey, what does this do instructions? Like for me, this was one of the most confusing ones. And what it does is, it makes a comparison between these two registers, S0 and T0. And if S0, in this case, if S0 is less than T0, T1 will be 1. You will set it. If it's not, T1 will be 0. So it's a binary result, actually, in the end. So after this instruction, T1 will be either 1 or 0. Now, why is this good? Well, it's good because then I can directly check if it is 0 with a branch equal in the next one. So what we are seeing here is one of those tricks that we end up using in MIPS. We could have a range of branch instructions. So we could say we have branch less than, we have branch less or equal, we have branch greater than, branch greater or equal, branch if you please, you know, whatever. The last one was a joke. There's nothing like that. Oh my God. Shut up, Frank. So instead of having a range of different instructions that react on it and make all of them be an I-type instruction, the idea behind this is, look, the equal and not equal we use a lot. So let's have an instruction for that. But then if I want to check something more elaborate, and you can easily see that if you have the SLT instruction, by combining SLT with BNE, BLE, BNE and BEQ, you can do all comparisons that are possible. So by using only 3 instructions, I can emulate the equivalent of 6 instructions. So I save 3. And, you know, those guys are going all broke for making sure that we keep things simple and have a limited number of instructions that we can execute very well. So once again, the way the SLT works is we are trying to compare the S0 with T0. If S0 is less than T0, this one will be 1. Otherwise, it will be 0. Meaning that if this condition no longer satisfies, this guy will be 0. These guys will, this branch equal will match and we will be done. Otherwise, we are jumping back in the loop and staying until we finish. Convinced? Okay. Here's a question. What type of instruction is SLT? Someone? R-type. Why? It uses 3 registers. We compare S0 with T0 and then write into T1. The specialty is T1 will not be, I mean, will just be the result either 1 or 0. And if you now go back into the lecture when we were talking about combinational logic, the very, very end, we had an ALU, and we showed that it can do addition, it can do subtraction, and or. And one of those instructions, if you go back in the slides, was this funny SLT. So we use the same ALU to make this comparison, because what we do is we subtract those two numbers and check if the result is negative. And you know that a negative number, what happens in a negative number? How do you realize a negative binary number? Exactly. So essentially, you end up subtracting them and copying the most significant bit into the destination register. So it's an easy operation. It's not a hardware-wise, it's not a complex operation, especially if your hardware is already implementing subtraction, because you need to subtract and then look at the MSB. Okay. There is general no mutiny in the class, which is good. Okay, so let's go into things that get slightly more interesting. Arrays and also structures. We want to, in programming, I don't need to tell you, you end up manipulating data that is located inside arrays of multiple dimensions. And the way that you access them, there's an index. The array size is determined by the size of the elements. But eventually, all of them will land in the memory. All of them will have an address associated with it. So let's use a very, very simple array. We only have 5 elements in this array because the slide is only that large. And we have a base address. And in our case, the base address is 12348000. And the first element, if it's a 32-bit value, is at this address. The next one, array 1 is here, array 2 is here, array 3 is here, array 4 is here. So if I have the base address, I can immediately say, hey, if I add 0 to it, it's the first one. If I add 4 to it, it's the next one. If I add 8 to it, it's the next one. So just by what I would need to do is have the base address somewhere. And once I have the base address, I can manipulate the rest of them a little bit more easily. So this is, let's say, a high level of code. And in the MIPS assembly code, I want that the base address is in S0. Now, here comes the interesting thing. The base address is 32 bits. How do I get 32 bits into a register if only I only have immediates? Right? No? I can do two things. I can load it and then shift it. Right? I can load the first 16 bits to the lower part and then shift it by 16 and then do something, right? Or I can use something more clever. And that, so let me just be clear before we go there. So this is my problem. So S0, if you look at S0, it is 32 bits. So this is 0, this is 15, 16, this is 31. 32 bits. Now, I want to initialize it so that it contains a 32-bit value. And sometimes I was writing that, hey, you know, the S0 has this value. And a couple of people asked, how do you do this? We had one example where we use something, a code like add immediate into S0, right? And then we were saying something like, what was it? 1, 2, 3, 4. So this is hex to at immediate. Sorry, 1. Something like this, right? So you're saying, hey, take whatever is in S0 and add the take whatever is in register 0 at this number and then make it happen here. Now, the funny thing is, this would only load it here, right? I had a person who was making thumbs up every now and then. Okay. He's very helpful. I think he's missing today. Okay, now, but if I want this, what happens if I want to put it here? I could do something which is kind of funny. I could say, let's shift this thing to left by 16. So I could do something like shift left S0 by, S0 by 16, something like that, so that this number gets 1, 2, 3, 4, 0, 0, 0, 0. I could do that. I first load it to the first 16, and then I shift it. Now I have a problem. Now I want to add here. I want to manipulate this part for the next one, right? What can I do? Technically, if you think about your combinational logic things, if I could OR a value on top of that, I could get it. So there is an instruction called OR immediate, $S0, $S0, and now this is the other number that I want to add. So I take this part, which is all zeros, I OR with this, and I write it back. And then this would magically turn into 800. So that's 1, 2, 3 steps. Can I take it after? Now, when people realize this and they said, you know what, we are doing this operation quite a bit. And let's not do it over multiple steps. Let's add an instruction that is called load upper immediate. So Louis. And then the Louis automatically sees this part and brings it. And then we can still do the OR E trick and add the 800 in here, 8,000 in here. Sorry, let me just switch to the next slide so that I have the code here. Yes. Yes, I even did it right. Sorry, he had the question first.
Why can we not just do an immediate also?
You could, but in some cases you want that you could. In this case, you could, yes. There are some cases where you don't want to or you want to manipulate only certain parts of it. That's where the OR immediate is very useful. So it's a very traditional way of doing it, but you could also add immediate to it. Sorry, there was another one. Same question. You'll see that there are multiple ways of doing exactly the same thing. They will result in the same thing. There are sometimes, let's say, historical preferences. There are sometimes things where they look at the cost of implementing it when the program is running, like how much energy is being consumed and things. And sometimes there are preferences saying, hey, this is an easier operation to do. This has less chances of causing pipeline stalls. We will see about that. And then they may prefer one operation over the other one. Okay, let's get rid of this. Sorry.
How can we divide the actual address into two in the assembly? Like here, those are like constants, but if you're trying to automate something, how can if you have an address in 32 bits, how can we divide? Is that like a specific operation?
Yeah, like this.
But you do it like by your hand, and it's like.
By my hand? I mean, I'm hoping that bless you. You weren't laughing at him, right? Okay, none of the assembly hopefully is done, or very few of the assembly is hopefully done manually by you by hand. This will get translated, the moment you see it here, it will get translated by the compiler to the assembly. There are some cases where die-hard people that want to extract every last bit of performance, knowing what the underlying architecture is, would write assembly code. If you are writing device drivers, if you are writing inner loops of some DSP kernels and things like that, you might want to do it in assembly. But 99-point-something% of the time, what you are going to be dealing with is this. The compiler will take care of it and translate it to there. So you have a 32-bit address, and you need to load it to something. He will emit these two instructions and divide the address into two.
So my question was basically that it's the job of the compiler to do that, because here it's like there's a constant address, there's not a variable or something, and then you just divide it by your hand. I mean, like it's done by somebody else, not in the assembly code itself. My question is there like a specific like free-coded function where we just give it like two bits and get 16 and 16 or something like that?
No, I mean, it will, hopefully, tomorrow at around 3:40, things will be clear, because we are going to come and explain how the entire tool chain comes together, okay? Very briefly. And then, if you're interested, I'm sure there are a lot of lectures and things that deal with the intricacies of this thing. But just continuing here I have my base address now, and the base address is S0. Now, if I want to have array 0, I know that this is base plus 0. I can do whatever I want. I load it from there. I operate on it. I write it back. Now, the second operation that I want to do is array 1. Well, I know where array 1 is. This is the base address. Array 1 is the next address. I load it into the register. I do whatever I need to do. In this case, I'm just multiplying by 2, and then I write it back. So all of a sudden, the thing that looked a bit weird makes a little bit more sense, because I want to be using something like that. I don't want to be constantly manipulating the register that holds the address. Add 4, subtract 4, if I'm going back and forth and trying to reach different values at around the same address. If I want to multiply the second entry and the third entry and write into the fourth entry, if I don't have something like this, I would have to constantly manipulate that base address back and forth, which would be very annoying because it's an additional instruction in between. Sort of convinced. Now, we can get cuter. What if my array is not that small, but my array is big, and I want to, put a loop around it and say, okay, here, this is my base address. In this case, the base address ended up being a completely different one, right? 23B8 and F00. And here is my loop, right? This is my endpoint. This is a trick that I used before. I'm trying to, this is my endpoint, the 1000, and S1 is my counter. So my counter is at 0. I will try to see if it is less than 1000. Well, as long as this thing is not set, I will, as long as this is not set, I will continue in this loop. If they are equal, meaning that if S1 is equal to T2, has already reached 1000, then I'm done. Now, which one am I accessing? In this case, I realize that I will be going through the array one by one, and I will be multiplying it with 8 and writing it back. Okay, say, I'll do it very easily. This trick is to come from the index that I have. This is the index. I need to go to the addresses. As you know, we are using word-based addresses, meaning that the next address is not 1 up, but 4 up. So this is my multiply by 4, so that I can manipulate my base address easily. I can go from array 0 to array 1 to array 2 to array 3. And if array 0 is at 23B8 F00, the next one is at F004, not at F001. I could have also done, alternative things, I could have also incremented it by 4, right? I could have done it that way. It's a choice in some points. And now I'm here. I'm trying to get the base address, and I'll add this index that I've calculated to the base address so that I can get a new base address, and I'm loading the array. This time the index is 0. I mean, it's just the address I calculated. I multiplied by 8. Multiplying by 8 is shifting left by 3. And I store this back. I increment the loop counter, and I go back to the beginning of the loop. I check, did I reach 1,000? If not, I stay here. So from something where things were very simple and, look not like a program that we would be writing, it's actually the same trick. We combine the two tricks that we had before with the for loop and the array addressing, and all of a sudden we realize that, hey, these are the things that are happening, and if this takes 1 nanosecond, 1, 2, 3, 4, 5, 6, 7, 8, 9 nanoseconds are needed to make one loop, right? So that effectively gives you how fast this program is running. And because most of the time is spent here, you don't really care that setting this thing up. You use 2 or 3 instructions. As long as you can keep the inner loops, let's say, somehow efficient, you'll be fine. Am I fine with time? Yes. Questions so far? Oh, yes, sorry.
The register contains the base address for the array. If you were to not use it for a while, it gets overwritten. Is there any way to get back to the array stuff?
Yes.
Is that just remembering?
There is the cool tricks. They are coming. I mean, we'll get cooler and cooler. We'll talk about stack, which is the greatest thing. It's not the greatest thing, but it's a fun thing. And it is coming very soon. Maybe even today. Okay. Now, any kind of interesting program that you make doesn't only have if, then, else, while, whatever kind of things, but also has some procedures, some functions, where you are in the main part of the program and you realize that, hey, I want to call a part of the program that is somewhere else. It's a part of a library, it's part of your program, it's a procedure that I call. And what happens is, you give it a number of parameters, and you expect the result to come back here. Afterwards, we will continue here. But in the meantime, the program execution jumps to this function. And this function may be called from many different places. It's not always this thing. The program may call the same function all over the place. And this thing then has, hey, I take 2 integers, and I will have a return value, and these return values will be a plus b. It could be very, very complex itself. It could call other functions, then could call other functions, could call other functions. My God, we could go completely apeshit here, okay? But how do we handle this? What's the idea? What's the procedure between that? Now, we have to distinguish between who called whom, because this is a bunch of instructions. This is a bunch of instructions somewhere in memory. They look identical. But the way that we define is the function, the caller is a procedure that calls the other one. That makes the other one the callee. I don't know if this is really English, but callee, okay. Not like border collie, but callee. Okay, now that we have identified the identity, let's just try to see. The caller has to pass some arguments to the function it's calling. There are very few functions that wouldn't need any arguments, but a lot of them do. And now you jump to the callee. The callee does the procedure, returns the result to the caller, and returns back to the same place it was called from. He has to know where it came from, because the same function could be called, you could be the callee of different callers. Not an exclusive relationship, okay? So the other problem is you must not overwrite anything, any of the state that the caller had. Like, that was maybe one of your questions. It's not necessarily exactly the same, but this is a case. You were doing a lot of things, you were using a lot of registers, and now you land somewhere else. And who knows what the caller had, what value was for T0, what value was for T7, and then other things. I shouldn't make any changes to it. And MIPS, because we have so many registers, says, okay, let's do some funny things. Number one, to call the procedure, because I'm going to do this a lot, what I need to do is I need to remember where the program was just before I called it. And normally, I would land at the next instruction, right? Somewhere in the memory, I was here. And if it wasn't the function call, I would land in the next instruction. And that one has an address. Jump and link is like a shortcut instruction that at once both jumps to the norm, to the next location, to the function, at the same time memorizes where it should return to. In a register that we call return address or RA. If we go back to the registers, let me see if I can manage this. Here. If you look at your registers, the RA, the procedure return address, is the special register number 31. Jump and link will store the next address that it would have normally gone to if there were no jump, would put it to the RA, while also manipulating the program counter to go to the location at which to the procedure in question. We will see a couple of examples tomorrow. We will slowly go through a relatively funny program to see how this works, okay? Don't worry, we'll see examples. Yes? Oh, don't worry, we will handle that. We will scale it, we will make it happen. Because no matter how much we put, I mean, if I put 2 return addresses, right, then the third one wouldn't work. So I have to have a solution, right? So, and we have a solution, it will come. Just a bit. Maybe tomorrow, let me see. Maybe tomorrow. Good reason to come tomorrow. Why? No. Okay. Or see in July. So, when we want to return from the procedure in the callee, just has to use the jump register instruction, because the RA, the return address, is already there the moment it enters, the program enters the callee. So you have your return address here, and you can just jump return $RA, brings you back to the location that you are supposed to go. Now, I have 4 registers to hold the argument variables. And then I have 1 return value. But how did we agree to this? Well, you know, we said there are a number of things, so let's have I have 2 return values. Look, V0 and V1. I have A0 to A3 for the arguments. This should be enough for most cases. If I need more, well, maybe I would have to reserve some place in memory and send a base address to there so that I can retrieve things from there. But for most cases, they are thinking these should be enough. So how does the procedure call work? This is what we had. This is a very, very simple function. We call the simple function no arguments and nothing done, just returns back. And then we continue the rest of the program saying A equals to B plus C. I know, it's very simple. But here, we also have the addresses now. Notice that the main part is here, and what he calls is jump and link simple. Now, when you make jump and link simple, the return address will hold the value 400204. Because if we weren't jumping, that would have been the next instruction that we would execute. In this case, once the simple function comes back, we want to be running A equals to B plus C, and hopefully S0, S1, and S2 are B and C, and S0 will be A. Okay? So now you come here, this is a simple, it doesn't do anything. We will have examples where things are longer, but once we are done, we are going to jump to register to RA. And the jump and link instruction already copied the return address, so it keeps things simple. This is again why they said it would make sense to sacrifice one instruction that does both saving the return address and jumping at the same time, because we end up doing this quite a bit. Okay, now let's add, yeah, so this is the explanation there, sorry. And now let's add some arguments. So these are conventions. This helps that when different people write software and compile it into MIPS, their things can be compatible. If everybody used registers like they wanted to, I mean, as long as people agree, there's no problem. Software written by one can be used also by the other one. So this is why there has to be some conventions. Now we are going to make it a little bit complex. We have 4 arguments, difference of sums, and what he will do is f plus g minus h plus I, and then f, g, h, I are the arguments, and you call it 2, 3, 4, 5, and hope to have the return come from here. How does it look? Well, a lot of code goes into there. Argument 0 goes into A0, argument 2 goes into A1, argument 3, blah, 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 blah. And then we do jump and link diff of sums. Now somewhere there is diff of sums, and we want to calculate these temporary variables. So there's T0 is A0 plus A1, F plus G. The other one is T1 is A2 plus A3, H plus I. Now I subtract T0 from T1 from T0. So this is this minus this, goes into S0. Now, let's say I was stupid. I put it to S0, but the convention is to make sure that it comes back in V0. So this is the way to move it. You say, okay, let me add S0 to 0 so that the result can be written to V0. Once again, an example of trying to save the type of the number of different instructions by using some configurations which have like you make an addition with 0, so you're essentially just moving from one register to the other one. Good so far? Now there are a couple of issues, and I will leave with the issues so that the solutions we can look at tomorrow. The issue is the following. If you look at the diff of sums, I ended up manipulating T0, T1, and S0. Now, what if T0, T1, and S0 were also being manipulated by the caller? The callee just overwrote those things, and is that okay? And what we will see tomorrow, and this is like, it goes back to the question that I received before. What happens if I need a more return address? If I call something, if this procedure calls something, the return address would be overwritten. So I need to store them somewhere. And the solution that is going to save our lives is to temporarily put those things that we have in our hands away. We will call it a stack. It's just like this poor guy. And we will, whenever we have something, we will just put it on top of the stack and say, okay, here's the location. Let's just put them here, we overwrite them. Once we are done, we take the ones back that we put and leave things as it is. Okay? And tomorrow, we will talk about this, and then we have a very cute recursive program, how it runs, to see also how to see the stack in action. Thanks a lot, and see most of you tomorrow.